Thank you all, and good morning. So these are my disclosures, which are not appropriate for here. So what we're going to be talking about is beyond the semen analysis, and what should we be doing now if we do see infertile men? What should we be offering them to really be state-of-the-art, cutting edge? We do know that the origin of the semen analysis is quite old. I'm not going to go through this, except that the first time sperm were seen under the microscope was in 1677. And then we jump here to 1929 when McComber and Sander published the first reference values for testosterone. 1929. And we have been looking at the same semen parameters, density, motility, sperm shape, now for close to 100 years, and very little has changed. Amazing. When you see our patients and give them the results of their semen analysis, the count, the motility, the morphology, they want to know, am I okay? Am I infertile? And that's not such an easy question to answer. It sounds easy, but it's not, because if you look at the average, and this is a study we did in Houston, we looked at a group of men in their reproductive years, and the average sperm count was about 81 million. So does that mean that the man sitting in front of you who has a sperm density of 40 million has infertility? And the answer is no. It just means he's a little left of center of some bell-shaped curve you're going to draw to define the normal population. But there are statistical limits. And right now, that's what we're dealing with. These were established by the World Health Organization through several iterations. This is what they did in 1999. And the sperm density, they said, should be above 20 million, the motility above 50%, and morphology above 30%. And that was morphology where they just eyeballed the sperm under the microscope and kind of approximated what the normal percentage was. And then we go to 2010. They changed it then. They said, no, the density is okay if it's above 15 million, motility above 40%. And now they're looking at strict morphology, they're actually staining the sperm and classify them. And they wanted them to be about 4% normal. And then just about 2 years ago, they came out with another iteration. And this is where they dropped the density a little bit to raise it actually to 16 million, motility 42%, and strict morphology 4%. And again, we're only talking about statistical limits. So that doesn't mean that the man who has 10 million sperm is actually going to be infertile. These are not functional tests. And if you look at these limits, actually in terms of are they going to have a baby, we find out that they're not predictive. Over on the right, you see we're looking at sperm concentration, the total motile count, the morphology, and the horizontal lines are normal versus low. And on the right, you see the actual statistics, and it shows they're not statistically significant. So whether it's low or high, it's not going to really predict very much. So the standard semen analysis has modest predictive value, if any, for live birth rates. So that we need new innovative tests, and that's what I'd like to focus on today. What's new? So this is a list of the tests. We talk a little bit more about morphology, DNA fragmentation. We're going to focus on epigenetic tests, 2 new ones, something that looks at actually the male reproductive cycle, and lastly, whole genome sequencing. And these tests are important in determining if fertilization will take place and if the embryo will grow normally. So talking a little bit about morphology, we know that many sperm will attach to an egg in an effort to penetrate the egg covering or the oolemma, but only sperm with a perfect lock and key shape or morphology will penetrate, and again, but only if they are activated. Only if they're ready to fertilize. That's called capacitation. So now we have a way of actually measuring capacitation. We can tell a man whether his sperm do capacitate in a normal fashion. This is called a CAP score. We do it quite frequently. We mail it out from our laboratory, but if you're seeing somebody and you're interested in running the test, you can just give them the website. We have little coupons, and they go on and they send them a kit at home. It evaluates the localization of a specific chemical, a ganglioside, that becomes effective when the sperm are capacitated. And what the company has shown is that the men should have greater than 27% normal capacitated sperm. I don't know if you can see this. This man has 11%, well below their data graph here, showing that he is going to have very significant problems with spontaneous fertilization. I say spontaneous because it's not going to affect the fertility if they do IVF, because they're going to be taking the sperm and sticking them into the egg. They don't have to be capacitated. A test that we do that measures functional capacity of the sperm is called the DNA fragmentation test. Most good laboratories do this. We know that the sperm of infertile men have increased levels of DNA damage. So every man has in his sperm production a percentage that are not absolutely normal. They have breaks in their DNA. And that's not significant unless they get above a certain limit. And the DNA damage is associated with impaired embryo cleavage, and it's also seen as unexplained infertility or repeated early miscarriage. So if we see a patient and we can't explain whether or not getting pregnant, or if they're getting pregnant and their wives are having spontaneous miscarriages, we will run this DNA fragmentation test. There's 4 different tests available. It's not important to know what they are. It's important to know that they all have the same endpoint, and that is the DNA fragmentation should not be above 30%. There are techniques to improve the DNA fragmentation. We know that a lot of it is caused by oxidants, and so we can give them antioxidants. And this DNA damage occurs after the sperm leave the testicle. It's called a downstream event. So you can give anti-inflammatories. We use NSAID sometimes. You can do a varicocele if the patient has a clinical varicocele. You will get improvement in the DNA fragmentation index, the DFI, but while it's statistically significant, to me, it's not really clinically significant. But we do know that if you use testicular sperm rather than ejaculated sperm, you are going to decrease the DNA fragmentation. And this is seen here in this article by Alvarez, where he compared men's DNA fragmentation in their testis tissue versus their ejaculate. And the bottom line is it went from 24% down to almost 5% if he used the testicular sperm. And this is something that we do fairly frequently in our laboratory and our clinic, but it's mainly for men who have failed IVF. I don't think we've ever done it just for high DNA fragmentation. We like to have failed IVF, and then we'll do testicular sperm with a cord block. It takes about 20 minutes and send this off to the IVF center. One of the newer and really exciting areas is epigenetic testing. And this is a new innovation for men who are seeking infertility care. This is the cover of Time magazine. And what is epigenetics? So epigenetics is the control mechanism of DNA and gene expression, totally independent of the DNA code. You see here on the cover of Time why your DNA isn't your destiny, and the reason they say that is because you can change epigenetics. So the genome that is relatively stable, you can change the DNA, but the epigenome can be modified by the environment. So if people have epigenetic caused defects in the quality of their sperm, you can look at their diet, stress, exercise, etc., change it, and you can actually change the gene expression. So it's an attractive target for study as well as manipulation in infertility. So the way the epigenetic control works, there's 2 different mechanisms. The one that we work with a group we have done research with out of Utah, is that it focuses on DNA methylation. So the methylation of sites on the epigenome is one mechanism of changing its expression. The modification of the DNA is caused by adding methyl groups to the epigenome. And the DNA methylation of promoter regions and genes can actually regulate gene expression. So if you have somebody who has hypermethylation, too much methylation, they lower their gene expression. Decreased methylation, they increase their gene expression. Remember, we're not changing the DNA, we're just changing the expression of what the DNA is encoding for. So the way this started is the company, the research lab that started this, took sperm from 43 fertile controls. These were men who had established pregnancies, and they identified the gene promoters within this group, within their sperm, with the most stable DNA methylation patterns across all of these men. They found over 1,000 that were very stable, and they included interesting gene promoters for embryo development and spermatogenesis. They just happened to find out that it was included. They then did a study using data from the NIH, and it was based on over 1,000 sperm samples. And they looked at the number of these already identified unstable promoters to assess the fertility potential of these men. And they established 3 classifications. So if the individuals had 0 to 5 unstable promoters, they had excellent fertility potential. 5 to 22, normal. But if you looked at the poor fertility potential, that was identified when they had 22 plus unstable promoters, all the way up to 1,000. And they also then looked at how does this impact outcomes in either IUI, intrauterine insemination, or in vitro fertilization. And what they found on the left here with IUI is it was very significant. So this would apply to natural conception as well, and that is individuals who were in the excellent, normal, or poor class was reflected in their pregnancy rate and their live birth rate. Very, very statistically significant to about the 5th decimal point. However, if you look at the success in IVF ICSI, had no impact. So again, no statistical differences in pregnancy and live birth rates between epigenetic results when using IVF and ICSI. But this is important because it tells the patient what their next move is. So it's a good test for infertile couples to decide if they should try or continue intrauterine insemination or go to the much more invasive and expensive IVF that is becoming so popular right now around the world. A fascinating test that has spun out of the same epigenetic laboratory is what's called NOA, non-obstructive azoospermic. It's a guide to treatment of sterile men. It's a novel epigenetic-based test to predict whether there's going to be sperm in that testicle. So non-obstructive azoospermia, NOA, is the total absence of sperm in the ejaculate. It affects 10 to 15% of men, but that adds up to 40 million men worldwide. Huge population. But if you look at the invasive, expensive surgical procedures such as microdissection testicular sperm extraction, what has to be done in the operating room with an operating microscope, used to extract sperm from the testicles of NOA patients, it's not that effective. Only 40-50% of the patients undergoing microtesting will really experience any significant amount of sperm that can be extracted. So a non-invasive diagnostic tool is really necessary to identify these men who are good candidates for these invasive procedures to increase the success rate by preventing unnecessary procedures. So we have worked with this company. I'm going to show some of the preliminary data. We looked at 18 testis biopsies on semen analysis, and 14 NOA patients providing semen analyses had to have a sperm extraction procedure to ultimately be utilized for the data analysis, either large bore testicular sperm extraction, clinical or conventional TESI, and lastly micro-TESI. And the methylation of sperm-specific genomic region was identified. So what the investigators did, like I showed you before with sperm QT, they identified a specific signature of epigenetic in these men that could be used in their semen to look for cell-free DNA. So the sperm-specific genetic region is different in sperm compared to all other tissue types. So it's only the cell-free DNA from sperm that will come up when they do this epigenetic testing. And this is cell-free DNA, so there's not a lot of it, but it still works in this assay. And it has this specific sperm signature which can be identified and quantified. This is some of the early data On the y-axis is the success of sperm extraction. On the x-axis, the percent of cell-free DNA in the sample. And as you see, as the cell-free DNA increases, so does the effectiveness of the ability to predict whether we're going to find sperm. And here it is again shown a little different way in a very early study. So on your right, you see the percent cell-free DNA, and then on the x-axis, you see the patients in whom we found sperm, and there was certainly enough cell-free DNA to characterize a prediction that was going to be positive, whereas with very little, if any, cell-free DNA, we did not find sperm. And this is an ongoing procedure. This is not yet available. It will be available, I'm predicting, within the next year or two, but they're still trying to iron out a little bit of the assay specificity so we get better results. This is a brand new test that we just started working with, and this test defines optimal sperm subpopulations by identifying sperm fertility windows. So what this company has done is to take semen samples, take an aliquot of 50 microliters, freeze the rest, and with that 50 microliters, looking at what I will show you is a specific identifier of sperm that are ready to fertilize, show that there is sequential, rhythmic maturation of these subpopulations that are ready to fertilize. So in other words, every 20 minutes, the semen may produce another subpopulation that is ready to go. So it's a new functional assay called Kinetex that quantitates this novel receptor, FCR, on the sperm head. And this is actually an immunological receptor, and I'm not quite sure of the biologic plausibility of what they're doing, but it does work. The FCR levels describe the readiness or the maturity of the sperm capable of fertilization, and the assay determines the presence of fertility windows or sequential times when these subpopulations of sperm should be used. So it measures the frequency and duration of these fertility windows. And what they've done, for instance, on the top, you see on the right, this is a normal, regularly cycling fertility window. So this is in that sample. They're going to take the sample and examine it every 15 minutes or every 30 minutes and demonstrate when the sample shows these windows, because that's when the sperm should be used. And then you can see what happens when it's an abnormal cycling. On the left, it just degrades. It looks good, but it doesn't hold up over time. The middle one has one cycle late. The lower one has one cycle early. And the lower bar shows that this individual has no cycling. So this could be a cause of his infertility. On the right, you can see these cycles of when the sperm are ready. When it dips down, that's when these sperm are ready to be used. And you can see when you look, so this is one with a pregnancy rate of 31%, and this is IUI, so that's a very acceptable pregnancy rate, intrauterine insemination. But you can see when they utilize the optimal window, they have a 31% pregnancy rate. And these other people, when they use suboptimal windows, they either get no fertilizations, no pregnancies, or 3%. So they're using this now in animal husbandry for inseminating cows using the bull semen only when they've identified these cycling windows, and it's improving the outcome in these insemination procedures. And one other thing which is really, really exciting, and that they can also utilize these windows, look at the bottom graph here, to predict whether or not they're going to have good embryos. So even with IVF, now if you utilize the sperm for ICSI that are in these optimized windows, they end up getting healthier blastocysts. And this is really exciting because there's no test like this available. Again, this is in the development stage, but we're working with them closely, and I think it's going to do really well. I want to end by talking about whole genome sequencing, or where we are now with regular genetics. This Tom Garcia, who runs our laboratory, does this as his area of focus. He has a NIH R01 grant for this, And, and I'm going to try to explain the technique as simply as I can because that's how I can understand it. I do not really understand. It's a very sophisticated technique, but what they do is they buy these nanopore filters, and these filters are actually membranes, electroresistant membranes, and they have tiny little microscopic holes in it, hence they're called nanopores. You can kind of see the little space between the blue bars over on the right. And what he does, he extracts the DNA and then layers it on, and each nanopore hole corresponds to its own electrode connected to a channel and sensor chip, which measures the electrical current that flows through the nanopore. So as these base pairs flow through, the nanopore filter identifies what the base pair is. So when a molecule passes through a nanopore, the current is disrupted and produces a characteristic squiggle, and these squiggles are then interpreted by an AI device that he has, and it actually prints out the entire genome, all the little letters, the 4 letters, but in all, the sequences, and that's fed into an AI algorithm that tells you which genes are abnormal. So this is the type of report we get, and if you'll see at the bottom, it's got 33 pages, and I'm just showing you the summary page. So what he can tell us whether it's got normal chromosomes, whether it's a normal XY or XXY male. He can tell us whether there's Y chromosome microdeletions, which is very significant in these azoospermic patients. And then it tells us the variance of significance in male infertility. And this one is a positive for some compound. I can't even read it. And then that particular compound is the genetic abnormality is interpreted and shows that it is a significant alterator of normal fertility. But he also then on the right shows the other variants in your genome. So if you're predisposed for cancer, it will print out these cancer genes. So one of the problems we're running into, as I was discussing with Dr. Kara, is now you have to tell the patients, we're going to run this test on you for your infertility, but you've had a genetic test that's demonstrated or may demonstrate some significant health impactful genetic abnormalities, and down the road, the insurance companies, when you're trying to get your insurance, your life insurance, may be able to get hold of these. So that's where we are. So what I've showed you is that the routine semen analysis is outdated and archaic. The semen analysis is not a test of fertility and cannot predict fertility treatment options. The semen analysis is a screening test. We're still using it. It's a good screening test for concentration, motility, and morphology, but many new tests are available and can be ordered directly from the biotech companies that make them. I've gone into detail about all of these. I think a really big future is whole genome sequencing. And lastly, I think we owe it to our infertility patients to offer them the latest in diagnostic testing. So thank you.